Good morning all. Last day you have learnt about the concept of GCD. You have found the GCD using prime factorization method, division method and in Euclidean algorithm method. And today we have some problems of GCD and how to find GCD of n numbers. That's in today's class. So first problem is, if a and b are two positive integers such that GCD of ab equal to d, then prove that GCD of a minus b equal to d. So given that GCD of ab equal to d, so by definition d divides a and d divides b. That's d is the common divisor of a and b, and d is the greatest common divisor of a and b. So since d divides a, we could write a equal to md, and d divides b, so b can be written as b equal to nd for some positive integers m and n. Then we could write a minus b is equal to md minus nd, which is equal to m minus n into d. We have to show that GCD of a minus b equal to d. So hence we got d divides a minus b, since a minus b is a multiple of d. So hence d divides a minus b. So d is a common divisor of a and a minus b. Now let c be an arbitrary integer such that c divides a and c divides a minus b. Now we have to show that d is the greatest common factor, that we have to show. So c divides a and c divides a minus b. So we could write a is equal to some alpha c and a minus b equal to some beta c for some integers alpha and beta. Then we could write b is equal to a minus of a minus b, which is equal to alpha c minus beta c, which is equal to alpha minus beta into c. Hence c is also a common factor of a and b. We have taken c is common factor of a and a minus b. From that we got c is a common factor of a and b. So by definition GCD should be hence by definition of GCD, c should be less than or equal to d. D should be the greatest common factor. So d should be the greatest one, c less than or equal to d. Thus any common divisor of a and a minus b is less than or equal to d. Hence d is a common divisor of a and a minus b, and any common divisor of a and a minus b is less than or equal to d. Therefore by definition of GCD, it's the GCD of a and a minus b, that is GCD of a and a minus b equal to d. Now we have the concept of Euclidean algorithm. So if we have two integers a and b, then there exist integers q and r such that a is equal to qb plus r, 0 less than or equal to r less than b. We can prove this theorem in the second module. We will learn the proof of this theorem. Now this is the problem. If k greater than 0, then GCD of ka kb equal to k into GCD of ab. To prove this, we are using the Euclidean algorithm, the system of equations in the Euclidean algorithm for finding the greatest common divisor of a and b as follows. We have a is equal to, when we divides b, we could write a is equal to q1b plus r1. By Euclidean algorithm we could write this one, that is the remainder is 0 less than or equal to r1 less than b. And next step we are doing the b equal to some q2 r1 plus r2, 0 less than or equal to r2 less than r1. Next we are doing r1 equal to q3 r2 plus r3, 0 less than or equal to r3 less than r2, etc. Rn minus 2 equal to q1 Rn minus 1 plus Rn, 0 less than or equal to Rn less than Rn minus 1. then Rn minus 1 is equal to Qn plus 1 Rn plus the remainder 0. So GCD of A and B is the last non-zero remainder. Rn is equal to Rn. Here the last non-zero remainder Rn. That is GCD of AB equal to Rn. Now we multiplied each equation of the system by K. So Ka is equal to Q1 into Kb plus Kr1, 0 less than or equal to Kr1 less than Kb. Kb is equal to Q2 Kr1 plus Kr2, so 0 less than or equal to Kr2 less than Kr1. Kr1 is equal to Q3 Kr2 plus Kr3, 0 less than or equal to Kr3 less than Kr2, etc. Krn minus 2 is equal to Q1 Krn minus 1 plus Krn, 0 less than or equal to Krn less than Krn minus 1. And Krn minus 1 is equal to Qn plus 1 Krn plus 0. We are multiplying each of this equation by K. So here Ka, Q1, Kb and Kr1, something like that. But we got, this is clearly Euclidean algorithm for finding greatest common divisor of K and Kb. Hence, the greatest common divisor of K and Kb is the last non-zero remainder. Here it is, last non-zero remainder is Krn. Therefore, Kb is equal to Krn, which is equal to Kab, K into GCD of AB. So this is the proof. Now the GCD of n positive integers. The GCD of n positive integers a1, a2, etc. an is the largest positive integer that divides each a. It is denoted by a1. We are in bracket a1, a2, etc. an. Theorem is let a1, a2, etc. an be n positive integers for n greater than or equal to 3, then the GCD of a1, a2, etc. an is equal to GCD of a1, a2, etc. an minus 1, an. So first you have to find the n minus 1 numbers GCD and take the GCD of next one. So this is that problem. Using recurrence relation, evaluate 14, 18, GCD of 14, 18, 21, 36, 48. So you have GCD of, you have to find GCD of 14, 18, 21, 36, 48. For that, take the, here 5 numbers are there. So first take first 4 numbers, 14, 18, 21, 36, GCD of that one and 48. Now to find that, to find the GCD of 4 numbers, take the first 3 numbers, 14, 18, 21, GCD of that one, 36, 48. Now to find the 3 numbers GCD, find the 2 numbers GCD, 14, 18 and 21. And we know that GCD of 14, 18, the common divisor is 2, 21, 36, 48. GCD of 14, 18 is 2. Now take 2, 21. GCD of 2, 21. Common divisor of 2 and 21 is 1. Now GCD of 1 and 36 is again 1 and GCD of 1 and 48 is 1. So the answer is the GCD of these 5 numbers is 1. Now you have an exercise to find the GCD of using recurrent relation. Evaluate GCD of 24, 28, 36 and 40. And then second problem, using recurrence relation, evaluate GCD of 12, 18, 28, 38 and 44. Do this exercise.